Let's get started. So our first speaker of this session today is Mark Safranek, and he'll be presenting Schnorr signatures are tightly secure in the ROM under a non-interactive assumption.
Thanks for coming in the morning. So this is joint work with Gavin Cho, Georg Fuchsbauer, and Adam O'Neill. And let me moderate our work by recalling the paradigm of provable security. So the idea is we want to reduce the security of a cryptographic scheme pi to the hardness of some problem P. And to show this, we want to show that for any efficient adversary that breaks the security of our scheme pi, we can construct another adversary that now uses this adversary to solve this problem P. And one motivation behind this approach is with such reduction, instead of having to crypt analyze some maybe complex notion of security for our primitive, we usually want these problems that capture the properties we need, but they can be simpler to analyze, and also we can use the same problem to establish security of multiple different schemes. So going back to our reduction, I call it B here, if the time it runs is roughly the same as the time needed by the adversary A, and it also succeeds with roughly the same probability, we call such reduction tight. And this is not just a theoretical concept, but as we'll see throughout the talk, it has important implications for practice, as first recognized by the works in the works by Vallari and Rogaway in the early 90s. So one nice property of a tight reduction is now if we want to instantiate our scheme pi in the real world, we need to fix some parameters such as the key length, and now we can base this choice solely on the hardness of this problem P and look at the best known attacks against this problem, and then we obtain concrete efficiency while still having a provable security that guarantees we can use the scheme. But unfortunately, for many schemes, and many of them are also used in practice, we only have loose reductions, meaning that our reduction, our adversary B, needs to spend much more effort than the adversary A, and this makes it much harder to justify the selection of key sizes and so on. And in this work, we will focus on the Schnorr signature scheme, which was introduced in the late 80s by Klaus-Peter Schnorr, and it's nowadays become my it's not working anymore. So nowadays it's one of the most widely deployed pieces in cryptography, and it's usually deployed in the form of the add-DSA scheme over twisted Edwards curves, which is also currently being standardized by NIST. So the nice, it's working. Okay, so the nice properties of Schnorr signatures is algebraic structure allowed to realize many advanced functionalities, such as threshold signatures, blind signatures, adapter signatures, and so on. And in terms of security for a signature scheme, the standard notion is existential unforgeability under an adaptive chosen message attack, or just unforgeability for short, which says that an adversary that gets the public key and access to signing oracle should not be able to come up with a fresh forgery on a message it hasn't obtained a signature on before. And in the case of Schnorr signatures, they are based on the hardness of the discrete logarithm problem, and they can be shown existentially unforgeable in the random oracle model. But as we will see, this will be a loose reduction. So let's now ask the question, if we want to use Schnorr signatures and deploy them in practice, let's say we are aiming for 128-bit security, how large should we choose the group order? So on the one hand, we have the answer by the practitioners who are a bit more optimistic. So they will say we need 256-bit groups, and they will justify this by considering the best known attack against Schnorr signatures, which is in actually breaking the discrete logarithm, and on twisted Edward curves, this runs in time order of square root of the group order. So this explains the more efficient, shorter groups for the scheme. But on the other hand, we have the theoreticians that will be a bit more cautious and conservative here and say, we should be careful, we don't know, maybe there could be other attacks. So let's consider provable security. So there is the result by Poincheval and Stern, where they give a loose reduction under the discrete logarithm in the random oracle. And as we see here, so the advantage or the hardness of discrete logarithm here is not direct upper bound, but we have QH, which is the number of hash queries the adversary makes times the square root of this advantage. And now if we, let's assume 2 to the 64 hash queries the adversary can make, if we now plug in these groups of order 768 bits, the best known attack again will be square root of that. So if you do the calculations here, we get exactly the bound of 2 to the minus 128 using our security proof and the guarantees we get here. And maybe one important remark here as well is if we plugged into these equations the suggestion by the practitioners, 256 bits, we would in fact obtain 0 bits of probable security. So you might be wondering who's right. It turns out it's quite a subtle question. I can't give a definitive answer because we simply don't know what the best known attack is, or if the best known really is the best attack. And we also don't know if the security proof we have, if it's maybe just an artifact of the security proof why we are losing, why it's loose. So the best we can hope for, and this also motivates our main question, because if that's possible, then this would resolve it. So can we have a tight security proof for Schnorr? And if so, under which assumption? So before going into details, let's consider the prior work. So in positive results, we have the original security proof that shows under discrete logarithm assumption in the random oracle model, Schnorr signatures are unforgeable. But unfortunately, this is not a tight reduction. So then subsequent works, the next two works here by Payet and Vergniaud, as well as by Bellari and Dye, they achieve tight or semi-tight reductions. So they improve the tightness of the proof. But to achieve this, they use much stronger assumptions. So they use now, instead of just discrete logarithm, variants such as OMDL, which are interactive, meaning that the adversary has also access to an oracle, and also non-falsifiable in the sense that even if you find an attack, you can't efficiently prove that this is an attack on the assumption. So these kind of assumptions are much harder to crypt analyze, and we would like to have simpler assumptions. There's another result that only uses discrete logarithm as the assumption, but now additional idealized models. In this case, by Fuchsbauer et al., they also use the AGM. So looking at these prior works in the last 20 years, you might be wondering, is it even possible? So there's a line of work that has led to the following possibility result, which says there can't be a tight and generic reduction from any representation independent non-interactive problem to unforgeability of Schnorr signatures. So let me explain what these terms mean. So a generic reduction just means that you treat the group as a black box and you only perform generic reduction steps, generic group operations in your reduction. And representation independent just means if you have a solution to your problem, it doesn't matter how you represent the group, this will always remain a solution. For example, a DL, if you know the D-log of a group element, will always be the correct answer no matter how you represent your group. So, and unfortunately, all our usual assumptions, such as DL, the Diffie-Hellman problems, Uber assumptions, all of them are representation independent. So this leads us to now a more specific question. If we want to get a tight reduction, is there a representation dependent assumption we could find, or a non-generic reduction we could use to get around these impossibilities? So before showing you what we came up with, let's introduce a Schnorr signature scheme. So it's defined over a cyclic group of order P and uses a hash function that maps into ZP. So key generation simply samples a fresh D-log instance as the public key, so some random group element, and then this D-log will be the secret key. If we want to sign a message, we choose this random little R value and compute G to the R So this big R will be the first component of the signature. Then we hash this together with the message to obtain a challenge. And then we take a linear combination of little r, C, and the secret key to compute this value X, and then R together with X are our signature. And to verify such a signature, we, as the verifier, can also, since we have R and M, we can compute this value C, and then we check well-formedness of the value S. But since we don't know X, this is done in the exponent of the group, so we use the verification key here. Yeah, so this G to the S equals R times VK to the C. You should remember it. This will be important also on the next slide. Because now, to introduce our new assumption, let's first have a look at the original discrete logarithm problem. So yeah, here the adversary gets a random group element and then needs to compute the discrete logarithm. So our assumption will now additionally rely on an arbitrary efficiently computable function f that maps from the group to ZP. And what now changes in our, we call it the circular discrete logarithm problem, is we still just get a discrete logarithm instance as our input. But then the goal now is to output a value R and Z, which looks basically like a Schnorr signature, such that f of R is non-zero, and we satisfy this equation here, which corresponds to the Schnorr verification equation. So the reason why we have this condition f of R should be zero is that if you use such a value, then clearly this solution will work for all values of H, and then for a concrete group, there could be an adversary that has this solution hard-coded. So that's why we have this check here. And also maybe the name circular comes from the fact that R appears here both as a factor and also in the exponent of this equation. All right, so let's see if this assumption has the properties we need. So clearly it's non-interactive. It's also falsifiable. You can efficiently check a solution. And importantly now, our new assumption is representation dependent, because since we're using this function f that maps from like the bit representation of a group element to ZP, if we change the representation, our evaluations will change, so the solutions will also change. So you might be wondering, does this correspond to simply assuming security of Schnorr? So clearly not unforgeability because it's non-interactive, but maybe this corresponds to assuming some no message attack on the empty message. But this is not the case because our function f here is independent of the hash function used by the actual scheme. So in fact, we just need a single function f for which this problem is hard. We don't even need to know exactly what this function is, and our security proof goes through. So using this assumption, we give the first tight reduction under a simple non-interactive falsifiable assumption, where you can see that the hardness of CDL bounds our security of Schnorr directly, together with this negligible term that depends on a number of signing and hash queries, and also the preimage, the size of the preimage set of 0 here. This comes from the fact that we don't allow, so f of R, right, needs to be non-zero. So this comes, we need to make sure that when we do a reduction that we can extract the CDL solution, which is a valid one. And yeah, I want to again stress this result holds for any function f here. So basically the function that minimizes this advantage will give us the best bound here. Next, we also want to show that our new assumption is applicable beyond just basic Schnorr signatures. So we considered the recent Sparkle plus Schnorr threshold signature scheme by Kreitz, Komlo, and Mahler, and try to use CDL here. So we might be asking, what is a threshold signature scheme? Think of it as a signature scheme where we distribute the secret key among n parties in a way that at least t of them, the threshold, needs to come together or needs to interact to sign a message. And this is as many applications. One could be securing crypto wallets. So instead of having a single point of failure, an attacker would need to compromise multiple parties and devices if we use the threshold signature scheme. And moreover, threshold signature schemes, especially for Schnorr, are a hot topic because they're being currently standardized by NIST. So in the original work, they show a loose reduction from the static security of Sparkle Plus to the discrete logarithm problem in the random oracle model. And we use CDL to obtain a similar result as for basic Schnorr signatures. So we are able to obtain a tight proof also of static security under CDL. So now that we've introduced this new assumption, giving us some nice results, you might be wondering, how hard is this new problem? So when justifying CDL, we carefully chose two different aspects and gave two different analysis. In the first one, we just idealized the group. In the second one, we idealized the function f. So our first result is in the elliptic curve GGM, which is a model proposed by Groff and Schub. We show that CDL is as hard as DL for any function f that has small preimage sets. And you can think of this as being quite natural. So in particular, an injective function or close to injective works very well. There's also an attack on our assumption if, let's say, f is just a constant. So yeah, in this idealized analysis, like in the idealized model, corresponds also with the S we would like to use. And then in the second result, we just idealize the function. So we now work over a standard group, but we use the algebraic bijective random oracle model introduced in prior work to analyze the ECDSA conversion function and the ECDSA signature scheme. And in this model, we show if we idealize the function in this way, that we can reduce CDL tightly to discrete logarithm. So it's as hard as discrete logarithm, basically. And in particular, this function, this ECDSA conversion function, is a good candidate for assumption. So the way it works, it takes an elliptic curve point and maps it to the reduced x coordinate. So it will be a 2-to-1 function, which is close to injective. All right, let me wrap up. So to summarize, we introduced this new assumption, the SQL discrete logarithm problem, a new non-interactive falsifiable variant of DL, which uses this function that maps from the group to ZP. We use it to show a tight reduction of unforgeability of Schnorr signatures in the random oracle model. And we conjecture that the ECDSA conversion function is a suitable candidate for hardness of this problem in suitable idealized models. Finally, we also use it to apply to this advanced primitive based on Schnorr, the Sparker+ scheme. So let me finish by giving some future directions and some open problems here. So first question would be, can we find any function for which CDL reduces to a standard assumption, maybe in the best case even directly to discrete logarithm? The second question would be, can we maybe use CDL for other advanced primitives based on Schnorr, such as adapter signatures, multi-signatures, blind signatures, and so on? And finally, the very big question is, could CDL maybe be helpful in instantiating Schnorr signatures under existential unforgeability in the standard model? Right, with that, thank you, and I'm happy to take any questions.
Do we have any questions?
No. Yeah, so it's still ongoing work. We are looking into other applications. Yeah. So far, we don't have a concrete scheme where we have a proof, but yeah.
Julian?
Oh yeah.
I have another question. Right, so for a lot of these newer schemes, right, so you need something like DDH to make it work. So does this have, like, can you use it together with DDH, or does it conflict somehow?
Yeah, so I think that would be an interesting idea. Maybe if you have a proof under, let's say, D-log and DDH or similar reduction, so maybe then you can.
Like circular D-log and DDH, right?
So you're asking if there's a variant of CDL for like DDH, or?
No, I'm even asking just like if these two assumptions, CDL and DDH, you know, if you can use them together, or if they're.
Yeah, we at least in like the best analysis that we have, which is using these idealized models, for both of them, I guess currently is the best attack would be solving discrete logarithms. So
okay,
at least
that might be interesting to.
Yeah, I think.
Forward.
Yeah.
Or
I
adaptive
really,
security,
we
maybe.
didn't have time to go through the proof details, but the key advantage here is that we don't have to rebind in the proof, using this assumption.
Okay, cool. Thank you.
Okay, let's thank the speaker again.
Can you hear me? Okay.
Okay, so our next speaker will be Renas Bacco, and he'll be presenting Teaspoon tightly secure 2-round multi-signatures with key aggregation.
Okay, yes, thank you for the introduction. So today I will talk about Teaspoon, which is a new tightly secure 2-round multi-signature with key aggregation. And this is joint work with Benedikt Wagner. I guess it's good that the previous talk really explained the importance of tightness, so I don't have to do that anymore. So we all know that tight signatures are important and nice, and yeah. So let me first introduce you to the notion of multi-signatures. So in a multi-signature, we have n parties, and each party has a public secret key pair, which it can just generate locally, so we don't assume any trusted setup or something like that. So we are on the plain public key model. And now say these parties want to assign a message M, and the idea of a multi-signature is to do that jointly and collectively so that the parties communicate over several rounds of communication and interaction. And at the end of the interaction, they output a signature, sigma. And ideally, of course, we want that the signature is short, so it is independent of the number of parties n. And now if we have this signature, we can verify it. And for verification, we always take the message, right? And we also take the list of public keys of all parties in order to verify the signature. And now you might think, okay, when we have, for instance, in the blockchain setting where we have thousands of parties, and then, I mean, if we have thousands of public keys, the verification becomes very expensive, right? And I mean, where do we store all these keys? And that is a problem often. And this is where the where the property of key aggregation for multi-signatures comes. So key aggregation allows to take this set of all public keys and combine them into a single compact public key. This one. And this single public key can then be used for the verification. And okay, so ideally we also want the multi-signature to have this property, but many or some multi-signatures don't have this property. Okay, so regarding the security notion of multi-signatures, I guess it's fairly standard. It's the normal unforgeability notion for digital signatures. So in the case of multi-signatures, what we want is we allow the adversary to corrupt all but one honest, like one party. So as long, and the idea is as long as we have at least one honest signer, the adversary cannot forge signatures. Okay, let me now tell you about like the objectives of multi-signatures. What do we care about in signatures? So in general, we care about security and efficiency, right? And what does that exactly mean in the case of multi-signatures? In the case of multi-signatures, because it's an interactive protocol over several rounds, we care about the round complexity, like how many rounds does it take to generate a single signature? And what is the communication between parties so that they output the signature in the end? Of course, we also care about the signature size and also the computation. And in terms of security, what we care about is, okay, it's a computational hardness assumption that we are relying on our security proof. And ideally, we want some standard assumption like CDH, DLOG, or DDH, right? And what we also care about is the tightness or security loss of this of the proof. Yeah, I guess the previous talk already explained the importance of that. And of course, we also care about the abilities of the adversary. Can he start concurrent sessions? How many parties can he corrupt, and so on. So in this talk, I will only talk about pairing-free multi-signatures and the discrete logarithm setting. So what is our goal? Okay, in terms of efficiency, we want ideally 2 rounds, right? I guess that's probably the best we can hope for in the pairing-free setting without any strong assumptions, like strong setup assumptions. And we also want key aggregation. And in terms of security, we want a tight security proof, right? And we also want to rely our security proof on a standard assumption like DDH, CDH, and so on. And of course, I mean, we also care about communication and so on, but I will not talk about that from now on. So let us look at the state of the art in the pairing-free setting for multi-signatures. So regarding 3 rounds, we have, I guess, many multi-signatures, which are quite good. For instance, like this Belare-Nevin multi-signature from 20 years. It relies on DDH, is tight and very efficient and so on, but it doesn't have the property of key aggregation. On the other hand, music from 6 years ago relies on DLOG and has key aggregation, but the security proof is highly non-tight because it uses rewinding. And from 4 years ago, we have a tight version of music, which essentially combines these 2 ideas to get a 3-round scheme, which is based on DDH, is tight, and has key aggregation. So it seems like in the setting of 3 rounds, we already have the best we can hope for, right? Let's look at the state of the art for 2-round schemes. So we have Music 2 from 4 years ago, which relies on on an interactive assumption, which is OMDL. And it has key aggregation, but the security proof is also highly non-tight. It even uses double rewinding. And now, I mean, from 2 years ago, Eurocrypt, we also have this very nice framework from Tessaro-Joux, where they essentially take Music 2 and Frost, and they apply a general framework to get rid of the OMDL assumption. And so they only rely on DLOG and have key aggregation, but also the proof is highly non-tight, as in the case for Music 2. And we have made a lot of progress. Like 2 years ago, we have this chopstick scheme from Eurocrypt, and it is a 2-round scheme which relies on DDH. And there are 2 variants of chopsticks. One is tight, but without key aggregation, and one is non-tight, but with key aggregation. So what we want is, we essentially want to improve upon chopsticks, right? To get DDH, tight, and key aggregation. But it seems like, I don't know, we are stuck or something like that. So can we even design such a tightly secured 2-round scheme with key aggregation? Or is it inherently impossible? Might be. So let me state our results. So in our paper, we designed Teaspoon, which is a new multi-signature. And Teaspoon has 2 rounds and key aggregation. And the security proof is tight and based on DDH. So let me also show you a comparison table of 2-round multi-signatures. Again, I only focus on pairing free setting. So here you can see the schemes. Here's our scheme, Teaspoon. Here you can see if the scheme supports key aggregation or not. Here you can see the underlying computational hardness assumption. Here you can see the security loss. And these ones are the tight schemes. And here you can see the communication and the number of field and group elements that are exchanged. And here's the signature size. You can have a look at it for 10 seconds, and then, yeah, I will go on. Okay, and let me now explain briefly our techniques, how we get that one. So the starting point is chopsticks. How does chopsticks work? It has 2 rounds. It has a commitment round and a response round. So each signer, that's the public key and secret key of a signer. And in the commitment round, a party commits to a nonce, RI, and the commitment, it makes use of a commitment key, which depends on the message. And in the response phase, we open this commitment and output a response, like SI. Okay, that's the idea of chopsticks. And crucially, like the commitment scheme, it's a dual mode commitment, so it has 2 modes of, it has 2 modes, a hiding mode and a binding mode. And these 2 modes are indistinguishable by DDH. And the idea is that, like very intuitively, that the hiding mode essentially gives you the property that there are many valid responses, like for one commitment, and like for one committed value. And in the binding mode, there is at most one valid response. And let me now explain how that helps the reduction and security proof in chopsticks. So the idea of the reduction is first to switch the keys into lossy key. And the idea of lossy key is essentially that there is no secret key. So there is only a public key and there is no valid corresponding secret key. And this is done via DDH. And now the reduction guesses the forgery message, M star. And what it does for the commitment scheme, it makes all commitments in hiding mode for the non-forgery message and for the forgery message in binding mode. And for the simulation, like outputting or simulating responses, what the reduction does, here in the hiding mode, it can use a trapdoor to output the responses, because there are many valid responses, so it can use a trapdoor to essentially output one of them. And for the forgery, since we have a lossy key, like the problem of outputting a valid response becomes a statistically hard problem. And so it's essentially impossible for the adversary, or statistically impossible, to output a valid response. And you can see that this idea of the reduction is based on a guessing argument, right? So we have a security loss, which is linear in the number of signing queries, QS. Now let me explain how our ideas, what our ideas are. So let me first explain our construction. So again, parties have a public key, secret key, right? And what we now do is essentially for each signing session, we have two sides of a commitment. And each party, like locally, just chooses one of these sides. Like we have two commitment keys, and each party chooses one of the commitment keys to commit to its nonce. And then, like the response phase is the same. We open the commitment and we output the response. How does that help in the security proof? Well, in the security proof, first of all, we again switch the key to lossy key. And what we now do is because we have two commitment keys, we make one of them in binding mode and one of them in hiding mode. And the reduction will always choose the hiding, the side of the commitment that is in the hiding mode, because that allows to simulate signatures as in chopsticks using a trapdoor. And for the forgery, we hope that the adversary chooses the side that is in binding mode, which happens with probability 1/2. And now we know, since we have a lossy key and like binding mode, outputting a response is a statistically hard problem, and we win. So that is the idea of our scheme and the security proof. And you can see that we get it tightly, right? Because we don't have any guessing argument or something like that anymore, because we make all keys in binding and hiding mode. Now you might ask, okay, if different signers choose different sides of the commitment, how can we aggregate the commitments? Like how can we output a multi-signature in the end? Because the commitment does not give any guarantees if we have different commitment keys. And how we resolve that issue is via a cool trick, which we call signer partition technique. And if you are interested in it, you can look into our paper. And yeah, with that, I would like to conclude, and I'm happy to hear questions.
Just wondering, what's your concrete efficiency gain versus prior schemes, in the sense that you're comparing to a different scheme, right? That maybe has a loose reduction. So if you set the parameters in like say music to according to the reduction that they have, and then you set your parameters in your scheme according to your type reduction, what's the?
Yeah, I mean, we also have a table for that in the paper. Guess it's on page, I don't know, 25 or something like that, where we also compare to all the schemes, like in terms of really concrete parameters. And I think our scheme does quite well, and it improves upon the others. But I don't know, I don't remember the details, but you can look at into the paper.
Any other questions?
I have a more technical question. So so do you have you said you derive the key for the commitment from the message, right?
Yeah.
Is that right? Okay. So but then, so you derive it for every message, you derive it fresh.
Yeah, right. Essentially, we have two sides. Like you essentially, I mean, the commitment key is computed using a random oracle on the message and the aggregated public key. But in our case, we use 0, comma message, comma aggregated public key for one side, and for the other 1, comma m, comma aggregate public key. And we also always make one hiding, one binding.
So I guess I'm wondering, yeah, okay. So for the forgery, right? Why is it true that Why is it true that the winning condition doesn't depend on the event that you choose the right side? Why are these two events independent?
I mean,
Maybe the adversary only wins if it picks the hiding side.
yeah, but we only, like, we win with probability 1/2, right? We have a security loss of 1/2.
Okay, so you have like a game before where you show like you can like
Yeah,
the
yeah,
adversary can't distinguish. Okay, that probably makes sense. Okay, yeah, maybe we can discuss it offline.
Yeah.
That's it. Thanks.
Okay, let's thank the speaker again. Franklin Harding, and he'll be presenting server-aided anonymous credentials.
Okay, thanks. So yeah, this is joint work with Champ, Anna, and Stefano. So the motivation for this project is this new regulation, which asks EU member states to provide a digital identity wallet to their citizens. It has this very ambitious timeline, and they also want it to use privacy-preserving techniques. So, for example, like if a EU member state issues a credential to somebody, and that person goes to some verifier and proves to them some fact, like they're over 21, the verifier shouldn't be able to identify the user from that showing. Okay, so the initial approach to accomplishing this was to use signed vector commitments. And you don't need to know exactly what that was or how that works, but so they solicited feedback from the community on this proposal. And in response, a group of cryptographers wrote this paper describing, pointing out that like this proposal has very weak privacy guarantees, and instead you should use anonymous credentials like as introduced by Chaum and instantiated by Kamenish and Lasinskia. Okay, so how would this EUDI wallet work with anonymous credentials? So there would be some public key for the EU. EU member state would issue a signature on some set of attributes. So this could be stuff like the user's age or name or other things. And then the user goes to a verifier. They can disclose some of the attributes in the clear, like this one A1, keep the rest secret, and then prove in zero knowledge that they have a signature on those attributes. And the verifier can just check that the proof is valid and any other predicate of the disclosed attributes. Okay, and the specific recommendation in this cryptographer's feedback paper was to use Bona, Boyan, and Shacham signatures. And the reason for that is because they have very small keys and signatures, and they also admit this super efficient zero knowledge proof strategy. And so the caveat to BBS is that it uses a pairing. And this turned out to be a big issue. So there was this informal response to the cryptographer's feedback paper from engineers working on EUDI. And yeah, so they point out that BBS needs this pairing friendly curve. There's no standardized pairing friendly curves, and there's very limited hardware and software support. And so it's just not going to work for them. And that's why in this talk, we focus on trying to get pairing free anonymous credentials. So there's actually already a proposal for how to accomplish this specifically for EUDI and specifically for BBS from this company called Orange. And they posit that BBS can be made pairing free if you can introduce some extra interaction. So yeah, what do they do in their paper? They call this idea BBS sharp. So what do? They first point out that there's already a pairing free version of BBS in this keyed verification setting where the issuer and the verifier are the same party. And this goes back to like a paper from Barkey et al. In 2016. And then their idea is to lift this keyed verification scheme to be publicly verifiable by adding some extra interaction. So the caveat is that there's, in this BBS sharp paper, there's kind of a limited formal model and limited security analysis. And they also use the algebraic group model. So we had two questions when we saw this paper. The first is, one, can we formalize this server-aided version of anonymous credentials and proof BBS sharp secure, potentially without the algebraic group model? And the second is, can we generically lift keyed verification schemes to be publicly verifiable through some generic construction? Okay. So yeah, so just so far, so the EU needs pairing free anonymous credentials. there's this nice option of BBS, but it requires a pairing. There's BBS Sharp proposal, which makes the pairing free. And so up next, I just want to give you some background on BBS and BBS Sharp, and then we'll get into our results. Okay, so you have a bilinear pairing E. The keygen algorithm for BBS produces a public key in the second group. And then you sign by sampling some nonce E, computing some algebraic hash C of the attributes. This vector of messages, I'll use attributes interchangeably, but and then the signature is 1 over X plus E times this algebraic hash and the nonce. And you verify by using the pairing to see if you can kind of reconstruct the algebraic hash. Okay, and I mentioned there's this really nice way of doing zero knowledge proofs of BBS signatures. So this is from Tessaro and Zhu. And their observation is that this verification equation on the left-hand side can be rewritten just using bilinearity, like in green here. And so if you define some group element B to be this algebraic hash C minus EA, and you create some zero knowledge proof of knowledge of your attributes M and your nonce E for these group elements A, B, and C, then you can think of A, B, C, and this proof pi as attesting to a BBS signature. And you can get a zero knowledge proof out of this by blinding A, B, and C and having pi prove knowledge of the blinding factors. Okay, so I mentioned earlier that you can make BBS pairing, you can make this zero knowledge proof pairing free already in the keyed verification setting. And the observation there is that all this green pairing check is really doing here is checking that X, so X being the secret key, times A equals B. And so in the keyed verification setting, you can just check that directly because you're the issuer, and so you know the secret key. So you don't need the pairing there. Okay, so how do you lift it to be pairing free? So like I said, their idea is they're going to introduce some extra interaction, and that's going to be in the form of having the server issue a proof. So first, this holder gets issued a BBS signature. They're going to construct this zero knowledge proof, A tilde, B tilde, C tilde, and this pi, which this is the re-randomized, or this is the randomized version, like I mentioned earlier. And then they're going to submit A tilde and B tilde to the issuer. The issuer is going to check this relationship, which the pairing was equivalently checking. And if that relation holds, they're going to issue this discrete log equivalence proof, send that to the holder, and then when the holder wants to go to a verifier, they can just submit this pi DLEQ, and this will allow the verifier to check basically what the pairing was checking but obviously without having to know the secret key. Okay, and because there's obviously a privacy issue here, if you do it exactly like this, because A tilde, B tilde are sent in the clear to the issuer and the verifier, so if they collude, they can kind of do some linking attack. They also propose in the BBS Sharp paper that you should use this oblivious DLEQ proof strategy from or Tessaro, Zavaruka, and Zhu to issue this DLEQ proof obliviously. So the issuer here wouldn't learn anything about A tilde, B tilde, or pi DLEQ. Okay. So that's BBS Sharp. I want to get into our results. So our first result is we introduced this server-aided anonymous credentials model, and we provide security definitions. And then we have this lifting theorem, which says that if you have specific kinds of keyed verification anonymous credential schemes, like as introduced by Chase, Michaeljohn, and Zavaruka, and you also have kind of a corresponding oblivious non-interactive proof issuance protocol, then you can, we have a generic construction which lets you get server-aided anonymous credentials. Okay, and then we instantiate this paradigm to get two practical constructions. So the first is essentially just this BBS Sharp idea. So it's secure under GAP QSDH in the ROM, and it also has statistical anonymity. And then we have this other construction, which is new, where we get a SAC, which is just unforgeable under DEH in the ROM and has computational anonymity. Okay. And so kind of the highlight of our results is we get the first practical anonymous credentials from standard pairing tree assumptions in the ROM only. And also, our construction is in some sense multi-show. So what is our formal model? So there's three parties: the issuer, the holder, and the verifier. In the first phase of communication, the holder wants to get a credential on some set of attributes M, and they should get a credential if their attributes satisfy some issuance predicate phi. And then there's also this helper protocol where the user or the holder inputs their attributes and this credential communicates with the server, and they get out this helper information aux. And then lastly, there's this showing protocol where their goal is to convince the verifier that they have some credential on some set of attributes which satisfy this showing predicate psi. And to do this, they kind of have to spend this helper information aux. Okay. So I want to point out first that this helper interaction is completely independent of your showing predicate. So you can query the helper at some point in time, not knowing exactly what showing predicate you want to prove later, and then just later decide that. Okay, and I also want to point out, so if you see this model, you might ask why I called it multi-show earlier, because it seems like if you want to do n showings, you need to spend these n pieces of auxiliary information, and so you need to make O of n queries to the issuer. And it's true that in that sense, it's not multi-show. But on the other hand, so we completely amortize this issuance phase, and this issuance phase can be really expensive depending on the issuance predicate which you're proving. So you can imagine you're like proving something about some general circuit, and this could be very expensive. But in our model, once you do this issuance phase, you can just query the helper many times to get these pieces of helper information through this really lightweight interaction, and then just spend them later at your leisure for whatever showing predicate you want. So how do we define unforgeability? So the adversary gets some public parameters and a public key, and they get access to this issuance oracle, where this issuance oracle uses an extractor. So we define unforgeability with respect to an extractor, and when the adversary queries this issuance oracle, we're going to extract from their first message these attributes. Then they also get access to this helper oracle. At the end, they produce some showing predicate psi star and a showing tau star, and we say they win if this showing is valid for this predicate which they specified, but none of the extracted attributes would have satisfied this predicate. One thing that's really important here, for which I'll kind of also mention later, is that nothing about the winning conditions are affected by how the adversary queries this helper oracle. And so in particular, this is not like a one more unforgeability style definition. And this turns out to be really important for proving security without relying on like the algebraic group model. Okay, and then anonymity is simpler. So we have this adversarial issuer and verifier. We just say that the scheme satisfies anonymity if no adversary can tell the difference between the honest holder and some simulator, where the simulator uses some trapdoor. They, in issuance, they don't get access to the attributes. In this helper, they don't get access to the attributes or the credential. And in showing, they don't get access to any of that or the helper information. Okay, so that's our formal model. Now I want to get into this lifting theorem. So I said that we need two things for the lifting theorem. The first is, which is this keyed verification anonymous credential scheme. So typically the syntax of that scheme would look something like this. So you create a showing, you send it to a verifier, and then the verifier uses the secret key to make sure that this showing satisfies some showing predicate psi. In our generic construction, we're gonna require like a slightly more specific syntax. So we're gonna say that the showing is split into these two algorithms, show key and show pub. Show key is just gonna get the attributes and the credential. It's gonna produce tau key. Show pub is additionally gonna get the showing predicate psi, produce some tau pub. You're gonna send these both over to the verifier. And then as you can imagine, the verification is also split into two parts. So this keyed part and this public part. The secret key is going to be used to verify tau key in this S4 key algorithm. Only the public key will be used in S4 pub, but it additionally gets the showing predicate psi. Okay. And then the other ingredient we need is this oblivious non-interactive proof issuance protocol, which kind of corresponds to the keyed verification scheme. And the best way to explain how it corresponds is just to get into our generic construction. So in our generic construction, the issuance is exactly the same as in the keyed verification scheme. Then in the helper, the user is going to invoke this KVAC show key algorithm to get tau key. And then what we want out of the oblivious proof issuance protocol is that the user gets a proof PyV, which kind of attests to SVER key outputting one with this tau key part of the showing. Okay, and this should be oblivious, meaning that the issuer shouldn't learn anything about tau key or the resulting proof PyV. Okay, so then just the last part of our generic construction is this showing protocol. And for this, user is going to invoke the show pub algorithm with tau key, this proof PyV, and their showing predicate psi. This will produce, so yeah, they send across tau key, tau pub, and PyV. And then you can use the public key in the showing predicate to verify tau pub. You don't exactly know how to verify tau key directly because you don't have the secret key of the issuer, but you can kind of verify it by proxy by checking PyV with the ONIP verification algorithm. So one kind of interesting thing here is that this helper acts as an oracle for your SVER key relation. So like because the proof system should be sound, so obviously you're not going to get proofs if you input false statements to that oblivious proof issuance or to that helper. And this kind of creates some like subtleties in our security analysis, which I'll get into later. And the other thing is that there are some other subtle requirements for the KVAC and the oblivious proof issuance schemes, which I don't get into here, but you can see the paper. Okay, and then we get two practical constructions. So the first of which is this BBS-based one. The KVAC is pretty much unchanged from this Barkey et al. One. The interesting thing is because of this issue I mentioned earlier where the helper kind of acts as an oracle for this keyed verification, this means we need to prove security with this restricted DDH oracle. And so we end up needing this gap QSDH assumption where there's this DDH oracle instead of just QSDH, which is usually all you need for the KVAC, the BBS KVAC. And then the oblivious proof issuance protocol. So this is pretty much the same as in these two prior works. So the Charitana Aparam, Tesaro Zhu blind signatures paper. So the keyed verification relation here is just this discrete log equivalence relation. And so our goal is to obliviously issue proofs that statements specified by the user are in this language. So the issuer is going to have this secret key X, generator G, and this group element W, capital W, which is generated through some transparent setup. So in the real world, nobody knows it's discrete log. And then the user has the statement A and B and the other elements specified here. So the first thing the user is going to do is randomize their statement A and B into A tilde B tilde, send this to the issuer. The issuer is going to check the relation, and then they're going to interact in this blinded sigma protocol, where at the end, the user is going to get this proof pi, which attests to the fact that either their statement is in this language or the issuer knows the discrete log of capital W. And so obviously in the real world, the first part of that statement holds, and then we just use the second to prove zero knowledge. The really cool thing about using this protocol in our construction is that typically you need the algebraic group model for unforgeability when you use this like blinded sigma protocol or proof technique. But because we don't do any like rate limiting or one more forgeability type thing in our forgeability game, we don't need unforgeability from this oblivious proof issuance protocol. And so we don't need the algebraic group model. Okay, and so yeah, then we also have this DDH-based construction. So it's based on the Chase, Michael, John, and Zavaruha KVAC. And the cool thing about this construction is it uses this twin DDH technique, and we were able to show that this gives us an oracle for keyed verification for free, so we don't need any like gap type assumption. It's a bit less efficient. And yeah, those are our results. Thank you very much.
We have time for a short question. Okay, I was just wondering if there were any other conditions that the EU has on a solution other than unlinkability?
Yeah, like I think like for example, they also want like some sort of device binding, so they want to make sure that people can't like copy credentials and give them to their friends or things like that. So yeah.
Okay, let's
Yeah.
thank the speaker again.
Oh.
Okay, so our last speaker will be Andrea Flamini, and he'll be presenting multi-holder anonymous credentials from BBS Signatures.
Thank you very much for the introduction. This is a joint work with Isa Lee from Barnard and Anna Lisianskaya from Brown. And the title is Multi-Holder Anonymous Credentials from BBS Signatures. Let me recall what are anonymous credentials that were introduced by Chaum in the 80s, and the first practical realization was done by Kamnish and Lisianskaya in 2001. And they are privacy-preserving digital credentials whose authorship can be cryptographically verified. Anonymous credentials are issued by issuers who give it to generate the credential and give it to the holder. The holder can store the credential and use it to prove claims about their identity. And they do it by generating verifiable presentations that are sent to verifiers. The verifier can verify the presentation, and if they trust the issuer who generated the credential, they will accept the claim of the holder. I said that those are privacy-preserving credentials because multiple presentations created by the holder using the same credentials are unlinkable, meaning that if an adversary controls a set of verifiers and controls even the issuer, they won't be able to realize if multiple presentations were generated using the same credential. And this is a very important privacy property that is also made explicit in the EIDAS regulation that describes how the new digital identity system that Europe will use must protect the privacy of their citizens. There are multiple frameworks that allow to generate anonymous credential, and the first one, and one of the most well-known, is the CL framework, presented by Kamnish and Lisianskaya in 2002. And the idea essentially here is that to design the anonymous credential scheme, you need to design a special signature scheme that supports efficient non-interactive zero-knowledge proofs. According to the framework, the issuer will, to generate a credential, signs the attributes that you want to give to the holder using this special signature scheme. And the credential will be structured as the signature and the attribute signed. The credential is given to the holder, and the holder can prove claims about its identity by revealing a subset of the attributes in the credential by generating an non-interactive zero-knowledge proof, where the witness is the credential and the statement are the revealed attribute and the public key of the issuer. The presentation will be structured as the statement and the proof. In the paper I'm presenting now, we define a new cryptographic primitive that we call multi-holder anonymous credential. And this is our first contribution, the first contribution of our paper. And the motivation behind that was to design a cryptographic schemes that allows to increase the security of storage of anonymous credentials to prevent identity theft. The idea here is that the issuer, instead of issuing an anonymous credential to a single holder, will generate an anonymous credential. It will divide it in shares, and the credential will be given to multiple holders. Each holder will have its share of credential, and in a similar way as it is done for threshold signatures. And whenever a threshold of the holders decide to create a presentation, this holder can execute a multi-party protocol that will produce in output a proof, and they will be able to generate a presentation that will be sent to the verifier. This is the idea. We are mostly interested in multi-holder anonymous credential schemes where the structure of the presentation is the same, of the multi-holder anonymous credential is the same as the structure of the credential that was divided in shares here. The reason is that those multi-holder anonymous credential schemes are like, this is nice because we can use the multi-holder anonymous credential scheme even when the issuer only issues anonymous credentials. And in this case, the holder who receives the anonymous credential can perform the sharing of the credential. And instead, on the verifier side, the verifier doesn't need to care if it is interacting with a single holder or with a multi-holder, because the presentation will be verified in the same way. In the paper, we also define the security and privacy properties for our scheme. And those are the correctness, the unlinkability, and the unforgeability of presentations that are essentially standard for anonymous credential schemes and that have been adapted for the multi-holder scenario. And we also defined another security property, which is the identifiable abort, that essentially guarantees honest holders that take part of the presentation protocol, that they will be able to identify a corrupted holder who tries to prevent the generation of a valid presentation. And this is useful because these holders can exclude the corrupted holders from following presentation protocol executions. In this presentation, I will focus only on the unforgeability of presentation because it has been the hardest property to prove in our construction that I will describe in the second part of the talk. The unforgeability property is captured via an experiment. And in this experiment, the adversary receives from the challenger the public parameters of the scheme and the public key of the issuer. Then it can start a training where it can send a polynomial number of queries for full credentials. And in this case, the challenger will generate the multi-holder anonymous credential for the attributes queried by the adversary, and it will give all the shares to the adversary. So the adversary can use these credentials to generate presentation on its own. The adversary can also send a query to the challenger for a partial credential. And in this case, the challenger will generate a multi-holder anonymous credential called target credential, of which the challenger will send only T-1 shares to the adversary, where T is the threshold needed to generate a presentation. With the target credential, with the shares of the target credential, the adversary can send a polynomial number of presentation queries to the challenger. And in this case, the adversary and the challenger will execute the presentation protocol for the target credential. And this is very similar to the unforgeability experiment for threshold signatures also. Then at the end of the training, the adversary will produce its forgery, and it will win the experiment if the presentation is valid. If it is not consistent with any of the full credentials that it was issued, because of course the adversary can generate a presentation using the full credentials. And if it is not consistent with any of the presentation queries that it has made, because again, the adversary can generate presentations with the support of the challenger who knows the other shares of the target credential. Okay, now I'd like to move to our instantiation. And before doing that, let me recall how the BBS anonymous credential scheme works and why it is important. BBS is an anonymous credential scheme based on the framework of Kamenisch and Lisianskaya, so it is a special signature with efficient non-interactive zero-knowledge proofs. It is a multi-message signature, meaning that it is possible to generate anonymous credentials for multiple attributes. The public key of the issuer is compact, and the signature and non-interactive zero-knowledge proof is efficient. It has been widely studied for more than 2 decades, and it is also the object of a standardization effort by the Centralized Identity Foundation and IRTF. Now I'll describe the BBS issuance and for the sake of simplicity and to keep the notation as simple as possible, I'll describe it for the issuance for a credential for a single attribute, because it will be more than enough to understand our contribution. In this case, the issuer, before starting its issuance activity, it must perform a setup where it generates a bilinear group, G1, G2, GT of prime order P with a pairing from G1 times G2 to GT. The public parameters will be a single element H1 in G1, since we consider anonymous credentials with a single attribute. And the key pair of the issuer will be given by a random element X in ZP, and the public key will be G2 to the X. To issue a credential, the issuer must assign the attribute that you want to give to the holder. And to do that, it will compute a commitment to the attribute in this way. It will sample E as a random element in ZP. And then it will compute A as the commitment to the power of 1 over X plus E. Then the BBS signature will be A and E, and the credential will be given by the signature and the attribute. Now I describe the algorithm to present a BBS credential, and I'll follow the presentation algorithm proposed by Tessar and Zhu at Eurocrypt 23. Again, to keep the notation simple, I'll consider the case of the full disclosure, because again, it will be enough to understand our contribution in our construction. In this case, since we consider the full disclosure, the holder will reveal the attributes in the credential, and it will keep hidden the signature, which is the other part of the credential. The non-interactive zero-knowledge proof is a Sigma protocol made non-interactive using Fiat-Shamir. And according to the Sigma protocol, the holder will randomize the signature material, computing A bar and B bar in this way, and then it will generate a zero-knowledge proof of knowledge of a representation of B bar with respect to the commitment and A bar. So the proof will be given by, the presentation will be given by the proof and the statement proof. Okay, now it's time to move to our construction. So the multi-holder anonymous credential scheme compatible with BBS, meaning that what we do is distribute a BBS credential among multiple holders, and the output of the presentation protocol will be structured as a presentation of the underlying BBS anonymous credential scheme. So to issue a credential, the issuer will generate the BBS credential, and then it will divide it in shares. And now here was the first issue that we needed to deal with. So understand how to divide in share a credential. And because we needed to find a way to have an efficient presentation protocol as a consequence of our sharing, and also have a sharing that could be applied to any BBS credential. So our idea was to compute a Shamir secret sharing of the value E of the BBS signature, which is a nice choice because the BBS signature is always kept hidden. So this means that this sharing can always be performed. The structure of the credential share is the following. Every holder will be given its own share of the value E. And then all these values will be given to every holder. The group elements A to the power of E, and all the A to the power of EI for every I in N, where N is the number of holders, and the attributes in the credential. The crucial observation here is that giving to every holder the value A to the power of E is just fine. It doesn't leak any information about the value of E, and this is very important to prove the unforgeability. Also, I'd like to say a few words about the structure of our shares of credential. Giving to every holder the values A to the power of E, it's important to achieve the identifiable abort property that I've mentioned before. Giving to every holder the value A to the power of E, it's very useful to obtain an efficient presentation protocol. And also in the paper, we describe an optimization that allows to make the credential share constant in size independently on the number of holders. Now we can move to the presentation protocol, and I will describe it, keeping it side by side with the presentation algorithm for BBS credentials for those who are not familiar with that. And I'll show you that with our protocol, the holders essentially compute the same operations in a multi-party fashion. So we will have one of the holders that will be a primary party who samples a random element R in ZP and will broadcast it to the other holders. This will allow them to compute A bar and B bar as it is done in the centralized presentation algorithm. However, note that here, the holder needs to know E to compute B bar, and that's the reason why it is important for the holders to know A to the power of E, because here they will compute B bar in a different way, but they will obtain the same distribution if they're honest. Now, the value B bar is divided in shares in a deterministic way based on the distribution, on the sharing of the value E, and every holder will be able to compute the B tilde i's of even the other parties. And then the holders will compute a non-interactive with zero knowledge proof of knowledge of a representation of their B tilde I with respect to a given basis that changes according to if the holder is the primary party or not. These non-interactive with zero knowledge proof of knowledge are computed in a coordinated fashion that will allow the holders to combine their proofs. And at the end, the combined proof will be proof of knowledge of a representation of B bar with respect to the right basis, as it happens for the as it happens in the centralized algorithm. So that's why we managed to generate a presentation that has the same structure. Before concluding, I'd like to say a few words about how we managed to prove the enforceability of our scheme. And in particular, the hardest part was to prove that an adversary, like the hardest part was to build a reduction for the adversary who manages to win the enforceability experiment, generating a forgery based on the target credential, where the target credential is the multi-holder anonymous credential of which it is given only T-1 shares in the enforceability experiment. And in the paper, we show a reduction to the discrete logarithm assumption. I'll give you just an overview so that you have an idea of how it works. And the details will be in the appendix of the slides for those who want to download it. The reduction receives the DLOG challenge, and it will generate the key pair of the issuer in a honest way. Instead, the public parameters will be generated, including a trapdoor based on the DLOG challenge. Then, since the reduction knows the secret key of the issuer, it can answer to full credential queries because it can generate signatures. So it can give to the adversary all the full credentials that it queries. But when it receives the query for the partial credential, our reduction will generate a target credential so that the underlying BBS signature will have as value E the DLOG of H with respect to G. And this can be done because, according to the way the public parameters have been generated. And it will be able to generate the share of credential to give to the adversary. And it will know some information about the shares of credential that the reduction controls. This will allow the reduction to answer to presentation queries by programming the random oracle. And at the end, the adversary will produce its forgery. The reduction will rewind the adversary to the moment it sent the query for the challenge included in the proof. And this will allow the reduction to extract the BBS signature that at this stage it didn't know. So learn the value E, that will be the answer to the DLOG challenger, to give to the DLOG challenger, because it is the DLOG of H with respect to G. This concludes my presentation. Thank you very much for your attention. Thanks to Isali for the Alice and Bob illustrations and Kubi project for funding my trip here. Thank you.
Any questions?
Presentation. I have maybe a very, perhaps a silly question, but I noticed that you're sampling elements from ZP and doing then exponentiation. So I was just wondering if it's fine when it's 0. Does it still work or something breaks? ZP contains
When R is 0.
R or E.
When R is 0, like all the A bar and B bar, it's
Nothing breaks. I still contain.
No, yeah, but probably there's need to like exclude the R0 probably.
Because you do commitment of the attributes and then exponent it to
like
R. They're
like,
they're on the left.
Like A bar is gonna be 1 in that case, right?
Yes, and C of
And-
A1 to the power of R is not a problem when R is 0.
when R is 0, also it's gonna become like 1.
But my question is if something breaks, it's
Yeah, but-
still,
No,
Still fine?
like, no, I guess it's like you have to, I should check better the details, but I guess that like it should be a problem because A bar and B bar then like
Right.
yeah, they wouldn't like match
Maybe-
the pairing, like they would satisfy the pairing equation, but probably this is a special case, but I'll check it later and maybe we can.
it should
follow
be
up,
maybe
yeah.
ZP star, but
Yeah.
I was just wondering. Okay,
Yeah,
thank you.
thank you.
Any other questions? Okay, let's thank the speaker again.
Thank you.